Okay, let's jump right into this explainer and pull back the curtain on the single most fundamental move that makes all quantum computing possible. If you've been hearing about all these massive quantum breakthroughs, cracking impossible codes, searching through endless haystacks of data, and it all just kind of feels like this impenetrable magic trick, well, you're in exactly the right place. Today, we're going to map this whole thing out visually. We're keeping it beautifully simple, kind of like a warm, beginner-friendly drawing right on a whiteboard. And we've really got to start by shattering a massive myth right out of the gate. See, people hear the phrase quantum gate and they immediately picture those tiny little switches inside a normal computer chip. The ones crunching ones and zeros into and, or, and not. But that picture is completely wrong. Quantum gates aren't tiny switches crunching bits at all. They're actually something much, much stranger. A quantum gate simply turns an arrow. Honestly, if you don't get this one fundamental move, the whole field just stays a total mystery.
So, let's look at idea 1. A gate is a rotation, not a calculation.
I want you to picture a perfect, completely smooth globe in your mind. Not the Earth with all its continents and mountains, just a pristine sphere. This is our quantum playing field. Now, the qubit is simply a single clean arrow pointing outward from the very center of this globe. If it points straight up at the North Pole, well, that means the qubit is a 0. Straight down at the South Pole, that means it's a 1. But here is the true quantum secret, the thing that changes everything. That arrow is allowed to point absolutely anywhere on the surface of the globe. It's not just stuck pointing straight up or straight down. Those everywhere else spots, those are the famous in-between states. So, what does a gate actually do? Let's take what we sometimes call the flip gate. Imagine we start at step 1, with our arrow pointing at the North Pole. So it's a 0. The gate simply grabs that arrow and rotates it a perfect half-turn, smoothly swinging it all the way down to step 3, the South Pole, making it a 1. Notice what we actually did here. We didn't check a value, delete it, and write the opposite value. Not at all. We just smoothly moved an arrow through physical space. And, there are other types of turns too, like the vertical twist. Imagine taking your globe and just giving it a spin right on its vertical axis. The poles themselves stay exactly where they are, right? So the 0 and the 1 look completely untouched. But this twist quietly changes the hidden relationship between them. And you'll want to hold on to that thought, because that hidden relationship turns out to be literally everything. But here's the part that breaks your brain. Think about the huge implications of this for a second. If every single gate is just a rotation, and rotation is fundamentally reversible, meaning you can always just grab the arrow and physically turn it back, then a quantum computer never actually destroys information the way a normal chip does. There's absolutely no scribbling over a value and losing what was originally there. Because we're just turning arrows, the computation is basically a rewritable dance. You can always perfectly rewind the music. Which brings us to idea 2, the Stargate that makes maybe out of yes. All right, now that we know how to spin the globe, we have to meet the most important turn of all. I like to call it the Stargate, though, okay, its official name is the Hadamard Gate. Picture a coin lying flat on a table. Heads up. That's a definite, certain answer. Now imagine you flick it so it's spinning on its edge, just a silver blur. While it spins, it isn't heads and it isn't tails. It is genuinely both possibilities held in perfect balance. That, right there, is superposition. It's only when it finally clatters down onto the table that it picks a face. Well, the Stargate does exactly that to our qubit. It rotates a dead certain 0 down to the equator of our globe, creating a perfect 50-50 blend of 0 and 1. This gate is basically the ultimate on-ramp to quantum. It creates superposition out of nothing but a totally plain starting value. And it is absolutely vital to emphasize this. Until your arrows are spinning perfectly on the equator, all you really have are incredibly expensive 0s and 1s. This single, repeatable turn from the pole to the equator, that's where the true quantum magic begins. But here's the part that breaks your brain. Just consider the number 300 for a second. Spin 1 coin and you've got 2 possibilities. Spin 2, you have 4. But if you spin just 300 coins at the exact same time, the number of combinations they hold simultaneously is larger than the number of atoms in the observable universe. Let that sink in. By applying the Stargate across many qubits, you open up a workspace so incredibly vast that no ordinary computer could ever even write it down, and your machine is now standing inside all of it, all at once. All right, moving on to idea 3. A program is choreography. So we have these amazing universe-sized rotations, but how on earth do we actually use these turns to get real work done? Well, if one gate is a turn, a quantum program is simply a sequence of turns. It's choreography. You line up these clean, precise rotations on your whiteboard. A flip here, a little twist there, a stargate to really open things up, and the arrow travels this beautifully choreographed path across the surface of the globe. But, this brings up a massive, completely obvious, nagging question. If the qubit is holding millions of possibilities all at once, but at the very end you can only look at it once and get a single, plain answer when the coin finally clatters down, what is the point? The second you measure it, that vast, beautiful superposition is totally ruined, so how is this actually useful to us?
Think of dropping 2 stones into a totally calm pond. Those in-between quantum states behave exactly like ripples in water. In the spots where a wave's crest meets a trough, the water just goes completely flat, right? They perfectly erase each other. But where a crest meets another crest, those ripples double up and reinforce each other.
That is interference, and a good quantum program actually choreographs the turns so that the paths leading to the wrong answers line up crest to trough, canceling themselves out into absolute silence. Meanwhile, the paths leading to the right answer reinforce each other, crest on crest. You're arranging the dance so that the interference does all the heavy lifting. That way, you're guaranteeing that only the correct answer is left standing when the coin finally lands.
But here's the part that breaks your brain. Speed comes from destruction, not search. A quantum computer absolutely does not get its power from trying everything at once like some brute force search engine. Nope. It gets its power from making almost everything cancel. The real art of quantum computing isn't exploring the haystack. It's engineering a wave that makes every single wrong needle in that haystack completely vanish.
So let's bring it all home. Wrapping up, the whole picture in 3 moves. Here is your rapid-fire cheat sheet for everything we just mapped out. 1. A gate isn't a logic chip crunching bits. It's a precise physical rotation of a qubit's arrow on a perfect globe. 2. The stargate takes dead certainty and spins it into a perfectly balanced superposition. It's the true on-ramp to quantum. And 3. A program is really just a choreography of these turns, meticulously arranged so the wrong answers cancel out by interference and the right one rings out loud and clear. But remember, every single gate we've drawn out today has only touched one qubit. Just one lonely arrow on its own little globe. The real spooky magic, that Einstein-bothering connection where 2 qubits share a single fate, that requires a gate that reaches across 2 qubits at the exact same time. So next time on our explainer, we're going to build that exact move, the controlled gate that forges entanglement.
Before we wrap up, though, I really want to hear directly from you. Which of these gates would you most want to see animated turning on the globe? The flip, the twist, or the stargate? Drop your thoughts in the comments below, and we'll explore the winning choreography in action next time. Thanks so much for expanding your mind with me today.